Welcome to this comprehensive guide on C# components, systems, and managers, which are fundamental concepts for building robust and efficient software architecture. These powerful design patterns are essential for creating organized and scalable applications, especially as projects grow in complexity. This focused design ensures high reusability across different entities and makes your codebase much easier to manage and understand. A component designed for health can be used by any entity that needs health, not just players. Understanding these concepts will significantly enhance your ability to design scalable and maintainable C# applications, whether you're working on games, enterprise software, or any other complex system. Mastering them will lead to cleaner code and more efficient development cycles. This video will break down each element individually, provide practical C# code examples that you can follow along with, and offer helpful tips specifically tailored for beginners. Our goal is to demystify these concepts and make them accessible to everyone. Let's begin our journey into building efficient and modular C# projects, exploring how these architectural patterns can transform your approach to software development. Prepare to unlock new levels of code organization and flexibility. Components are essentially containers for data, holding specific attributes or states for an entity, such as a player or an item. They are pure data structures, designed to describe what an entity is or what properties it possesses at any given moment. They are designed to be small, focused, and highly reusable, representing a single, distinct aspect of an object or entity. This singular focus ensures that each component has a clear purpose and can be easily combined with others to form complex behaviors. Think of them as individual building blocks that define what an entity has or is without dictating how those properties are used. For example, an entity might have a position, have health, or be renderable. For instance, a player health component would simply store the player's current health value, perhaps an integer, and its maximum health capacity. It wouldn't contain any logic for taking damage or healing, just the raw data. Here's a simple C# example demonstrating how you might define a player health component. As you can see, it's a straightforward class containing only public fields or properties to hold its data. Notice how it only contains data, specifically current health and max health, without any complex logic or methods that perform actions. This strict adherence to data-only design is crucial for component effectiveness. A key tip for effective components is to keep them extremely focused on a single piece of data or a very specific concern. This means avoiding the temptation to bundle unrelated data or behaviors into one component. Avoid adding behavior or methods that don't directly relate to the data it holds, such as take damage or heal. These actions belong elsewhere, ensuring your components remain pure data containers. This focused design ensures high reusability across different entities and makes your codebase much easier to manage and understand. A component designed for health can be used by any entity that needs health, not just players. By adhering to this principle of single responsibility, you create a flexible and extensible architecture where new features can be added by simply combining existing components or creating new, small ones. This promotes rapid development and iteration. Next, let's explore how systems bring these data containers to life by processing their information and enacting changes. Systems are where the actual work and logic of your application reside. Systems are the logic that operates on components, transforming their data or reacting to their states, effectively defining the behavior of your entities. They are the active part of the architecture, performing computations and state changes. They typically iterate over entities that possess a specific set of components, applying their logic only to those relevant entities. This allows for highly efficient processing, as systems only interact with the data they need. For example, a damage system would find all entities with a player health component and apply damage to them based on game rules or events. It acts as the processing unit for all damage-related operations. Here's a C# code example of a damage system that demonstrates how it interacts with our previously defined player health component. This illustrates the clear separation between data and logic. This system takes a player health component instance and an integer damage value as parameters. It's designed to be generic enough to apply damage to any entity possessing a player health component. It then directly modifies the current health property of that component, reducing it by the specified damage amount. The system doesn't store health itself. It merely acts upon the health data provided by the component. Systems promote a crucial concept in software design: separation of concerns. This means that different parts of your application handle distinct, non-overlapping responsibilities, leading to a more organized codebase. The data, encapsulated within components, is kept entirely separate from the logic, which resides within systems that operates on it. This clear division prevents tight coupling and makes each part independently understandable. This separation makes your code significantly more modular, easier to test in isolation, and much simpler to debug when issues arise. Each system can be tested independently, ensuring its logic functions correctly. When a bug occurs, you can often pinpoint whether it's a data integrity issue within a component or a logical flaw within a system. This focused debugging approach saves valuable development time and reduces frustration. This clear distinction between data and logic streamlines the development process significantly, allowing teams to work on different aspects of the application concurrently without stepping on each other's toes. It fosters collaboration and efficiency. Now, let's see how managers orchestrate these components and systems, acting as the conductors of your application's entire architecture. Managers are responsible for the overall flow and coordination. Managers are classes responsible for coordinating systems, managing the life cycle of entities and components, and handling global application states. They are the glue that holds the entire architecture together, ensuring smooth operation. They act as the central hub, ensuring everything runs smoothly by initializing, updating, and disposing of various parts of your application. Managers provide a single point of control for complex interactions. A game manager is a common example in game development, handling crucial tasks like game initialization, managing the main update loop, and overseeing the overall game state. It's the brain of your application. Here's a C# code example of a game manager that demonstrates how it might initialize and update our systems, such as the damage system. This shows how managers bring systems into existence and control their execution. The game manager would typically instantiate the damage system and potentially many other systems during its initialization phase. It's responsible for setting up the operational environment for all systems. Its update method, which is called repeatedly, would then iterate through and call the update methods of all registered systems. This ensures that all game logic is processed in a controlled and predictable order every frame. Managers provide a clear and singular entry point for your application's logic, making it easy to understand where the main execution flow begins and how different parts are connected. This simplifies onboarding for new developers. They centralize control, making it significantly easier to manage dependencies between different systems and to control the overall flow of your application. This prevents systems from directly depending on each other, reducing coupling. This structured approach helps prevent the dreaded spaghetti code and promotes a clean, hierarchical design that is easy to navigate and extend. It ensures that your code base remains organized even as it grows. By effectively using managers, you ensure a well-ordered and predictable execution environment, which is critical for debugging and maintaining complex applications. You gain a clear understanding of when and how different parts of your code are executed. Now, let's see how these three essential elements, components, systems, and managers, collaborate seamlessly in a real-world scenario to create dynamic and interactive application behavior. This is where the power of the architecture truly shines. Understanding the intricate interplay between components, systems, and managers is crucial for building robust, scalable, and maintainable applications. This synergy is what makes the architecture so effective in managing complexity. Imagine a simple game loop where a player character takes damage from an enemy attack. We'll trace the flow of information and logic through our architectural pattern to see how it's handled. First, an entity representing the player would possess a player health component, which simply stores its current and maximum health values. This component is purely data, holding the player's vital statistics. When damage occurs, perhaps triggered by a collision or an enemy's attack, the game manager would orchestrate the process. It acts as the central dispatcher, receiving the event and delegating the appropriate action. It would then call the apply damage method on the damage system, passing along the player's player health component and the specific damage value. The manager doesn't know how damage is applied, only that it needs to be. The damage system then takes this information and updates the current health property directly within the player health component. It's the system's responsibility to modify the data based on its logic. This entire interaction, from the damage event to the health update, happens efficiently within the game manager's main update loop, ensuring consistent and timely processing of game events. This loop is the heartbeat of your application. Here's a simplified C# code snippet illustrating this interaction, showing how the game manager invokes the damage system with the relevant component and damage value. This provides a concrete example of the flow. In this analogy, the game manager acts as the conductor, directing the overall performance. The damage system is the skilled performer, executing the specific action of applying damage. And the player health component is the instrument, holding the data that is acted upon. This clear separation of roles and responsibilities makes the system highly maintainable, as changes to one part are less likely to affect others, and incredibly scalable, allowing for easy addition of new features. You can swap out systems or add components without breaking existing code. Visualizing this data flow and the distinct responsibilities of each element helps solidify your understanding of this powerful architectural pattern. It's a mental model that will serve you well in complex projects. Each part has a distinct and well-defined responsibility, contributing to a cohesive and functional whole without unnecessary interdependencies. This modularity is a cornerstone of good software design. This architecture is incredibly powerful for managing complexity in larger projects, allowing multiple developers to work on different features simultaneously with minimal conflicts. It's a proven method for building robust and extensible software. In summary, components are passive data containers, systems are the active logic that processes that data, and managers are the orchestrators that coordinate everything, ensuring smooth operation. These three pillars form a solid foundation. This architectural pattern consistently promotes modularity, making your code easier to understand and modify, enhances reusability of components and systems, and significantly improves overall maintainability of your codebase. These are invaluable benefits for any project. For beginners, a great starting point is to design your components to be as simple and data-focused as possible, resisting the urge to add any behavior. Focus purely on what data an entity needs to hold. Then, build systems that operate on these components, ensuring they don't hold their own state, but rather process the data passed to them. This keeps systems lean and focused on their specific logic. Finally, use managers to tie everything together, handling the crucial tasks of initialization, managing the main update loop, and coordinating interactions between various systems. They are your central control unit. Practice by refactoring existing code bases to adopt this architecture or by starting small, new projects with these principles in mind. Hands-on experience is the best way to internalize these concepts and see their benefits firsthand. The benefits in terms of code organization, flexibility, and scalability will become evident quickly as your projects grow in size and complexity. You'll find your development process becomes much smoother and more enjoyable. Thank you for watching this comprehensive guide on C# components, systems, and managers. We hope this video has provided you with a solid foundation for building better software. Happy coding!